Okay. I thank the organizers for the invitation. So I'll talk about, I'm kind of tired of talking about exclusion processes to this audience, so I thought I'll tell you something more from the integrability side. So this is joint work with Roger Berend at Cardiff and Ilse Fischer at Vienna. So the model is, the original model is kind of classical. It's one of the classical integrable models. So if you have not seen the square ice or six-vertex model, here's a quick introduction. So you are on a subset of Z2. For each edge, you assign an arrow. If it's a horizontal edge, you pick either left or right. Vertical, you pick up or down. Such that there is local kind of conservation in the sense that for every vertex, there are exactly 2 arrows coming in and 2 arrows going out. Then an elementary combinatorial argument tells you that there are exactly 6 possibilities, and then therefore it's called the 6-vertex model. This is a kind of toy model for ice in the following sense. So here's this picture. So you put the oxygen atoms on your vertices, hydrogen atoms on the midpoints of the edges. Okay, for every such edge and every such vertex, and you imagine that the hydrogen is connected to the oxygen in the direction of the arrow, because there are 2 incoming arrows at each vertex. You'll have exactly 2 hydrogens connected to each oxygen. The other 2 you can think of as hydrogen bonds, if you like. So this is like a 2-dimensional version of ice, and this has the advantage of being exactly solvable. So what we are going to do is kind of slightly different. So we are going to take these kind of triangular subsets of the square grid. So I will need to refer to this later. So I'll draw a toy model. So what you want to do, what I want to do, is to assign arrows at these edges, obeying what is typically known as the ice rule. So the ice rule says there are 2 incoming and 2 outgoing at every vertex. We put the boundary condition that on the topmost edge, everything points upwards. So that's what I wrote over here. There are these parameters that will play a role in the computation. So here's an example. The top arrows are all vertical, and at each bulk vertex, you satisfy this condition. So notice that at the boundaries, there is no conservation rule. Okay, so it's possible for 2 outgoing edges to be at the boundary, or 2 incoming, or 1 incoming, 1 outgoing. Okay, so now we want to assign weights. So it's a statistical mechanical model, so you want to assign weights. So the weights are related to these indeterminates ui's. So to each path which starts, which goes like so, you assign the same weight ui. So u1 for this, u2 for this, and so on. And you have some boundary parameters, many of them. And for every vertex, you get a weight which is the product of the weights of the edges that are incident to it. So for example, this fellow gets a weight u5 from this path and a weight u2 from this path, so it has weight u2u. Okay. Okay, so the model has many parameters and it can be quite confusing, so I'm spending some time on it. So the weight, so to each vertex there will be a weight. The weight is given by the local configuration at that vertex. So there are 6 possibilities in the bulk. And there are some symmetries. So just for convenience, we have this shorthand notation u bar for u inverse and sigma of u for u minus u bar. And then you have this complicated set of weights, and there's no reason for you to I mean, there's no a priori reason for you to think that these are natural weights in any way. It's just the underlying mathematical integrability structure is what kind of forces us to choose these weights. And for example, the weight of that single configuration I gave you earlier has this, quite complicated looking form. And so the weight of a configuration is the product of all its edge weight, of all its vertex weights. And the partition function is the sum over the weights of all such configurations. So the aim of our of our work is to give you determinantal formulas for the partition function. So these are a priori not obvious at all. So the first result in this direction was obtained by my collaborators. So you want to count, so this is also, you can think of this as a combinatorial problem. You want to count how many such six-vertex configurations are there on this kind of subset of the square lattice. And then you need to choose the parameters in some way, and you need to choose this parameter q, which pervades everything. For example, there's a q in every single weight. You choose it to be the 6th root of 12th root of identity. And then the following result was proved by my collaborators in the advances in 2017. You have this very beautiful determinant formula when you set the middle parameter un plus 1 to be 1. And this allowed them to prove that the number of six-vertex configurations is given by this really elementary looking product formula. But this was conjectured by Dave Robbins as early as the mid-80s. But this was only settled more than 20 years ago, just now. So this paper recently won the Robbins Prize of the American Mathematical Society, which is given once every 3 years, and it's a major achievement in the field. So what we, motivated by some combinatorial blah blah, which I don't want to get into, we considered boundary specializations as follows. So there are two of them. So in the first one, what we do is we force the leftmost horizontal edge, to point to the right, and the rightmost horizontal edge to point to the left. So we place that as a boundary constraint, and we want to count the number, or we want to calculate the partition function under that boundary condition. So we find again, so this is our work. So we find again very nice determinantal formulas for these. And in fact, this determinant appeared earlier and is well known as the Izergin-Korepin determinant. It's actually the same determinant that appears when you consider again the six-vertex model on a square grid with so-called domain wall boundary conditions. So you force all upward edges to point, all vertical edge boundary edges to point outwards, and all horizontal edges point inwards, and you amazingly get the same determinant, the exact same thing. One thing to notice is that the number of vertices is also the same, but there's no obvious reason why this will be true. And this allows us to prove also that the cardinality is given by this beautiful product formula, which is also the same as the number of six-vertex configurations in this domain. The other specialization is that the leftmost and rightmost vertical edges point upwards. That's the other kind of boundary specialization. And again, without getting too much detail, we find the determinantal formula, and therefore, after specialization, we find this nice product formula, and this appears in some enumeration problems involving plane partitions, completely unexpected, and there's no clear answer for why this is the case. And yeah, so you might notice that this has been on the archive last 2016. That just tells you the timeline of publications in the mathematical sciences. So proof ideas in 3 seconds. You basically need the Yang-Baxter equation. There's some left-right equations. There's some non-obvious symmetries that you need to prove. And you basically argue by uniqueness of certain Laurent polynomials. Okay, so I'll stop.
Time for questions.
So, square eyes caught my attention. There is a lot of controversy in the literature. Last year, Andre Gaim published a paper in Nature showing existence of square eyes, but nobody can reproduce.
Okay.
So now you have exact partition function. Can you calculate entropy of this model, square eyes phase?
Yeah, so for the square eyes on the domain wall, the phase diagram is known. I forget who is somebody in UIUC who has done. So so this is well known. I mean, Herbert Spohn was here; he knows all these things. So there's some complicated phase diagram. There's something like that. I don't remember the.
No, I am asking that. Can you calculate entropy from your partition function? That I did not follow other.
I think they have done it, but
Who has done it?
I forget the name. I'll tell you the reference. Yeah, I think it's well known. Yeah. So this has been known for at least a decade. Yes, sir. No, not really. No. There's yeah, sure. So, but no, it's not wrong, obviously. But no. So the way one wants to think about this is that the boundary conditions are macroscopic. I mean, so one way to think about these things is in terms of height functions. So you have what you're placing. For example, you are trying to look at a sheet, and if you have free boundary condition, the sheet will look like so. But if you pin your sheet such that there are macroscopic changes across the system, then of course the sheet will look different. So I think this kind of thing is well understood. So it's equilibrium, and the boundary affects it, but that's only because the boundary is not just microscopic changes, but real macroscopic changes. Is that what you are also asking, Prabal? No, I think it's known. Yeah, I'll dig up the reference. Yeah, I don't remember the name. Okay, sure. Let's talk about it. Yeah.